Hello. So today we will be talking about something new, which is about the gradient, divergence, and curl. So far, what had we done? We had studied about vector functions, but when there was only one variable. Okay, so we had been studying vector functions of a single variable, but there can be vector functions uh, or even scalar functions of many variables. Okay, let me just give you an example. Okay, I will first explain what is the gradient, what does it give, what is the divergence, and what is the curl. One thing that you must remember when talking about all of these things is it is something that is relating to change. Whenever there is the word change in mathematics, you will be using the derivatives or even partial derivatives. Okay, so let us just go ahead with it. Okay, this is a very interesting topic, at least for me. I used to find it interesting. So let's see. Okay, let us talk first about the gradient. Now, just imagine that you have a metal object, okay, a box like this, okay, but it is made of metal and it is not hollow inside, it is completely filled. Okay, so what we are going to do with this metal box, okay, just imagine that it is metal and it is completely solid. Okay, just imagine that you are okay, so you are heating heating the box from this point. Okay, maybe somewhere over here you are heating it at this point. Okay, just have a lighter. Imagine that this one is made of metal. You are heating it. The heat, okay, so this metal object, it will be this metal object, okay, there will be a change in temperature, but the temperature will not be the same at each and every point. For example, at this point where we are heating it, the temperature is indeed very high, but for the points, for other points, the heat or the temperature may be different. Okay, because we will be measuring heat, okay, maybe in terms of temperature. One thing that we are clear from that is that when we are studying about the gradient, first of all, we will need a scalar function. Okay, you will need a scalar function. Okay, so over here, what is the scalar function? The scalar function in our example was temperature. Temperature is a scalar quantity. Okay, so again, okay, maybe let us just draw it. Okay, so we were having that square box. So sorry, okay, we were having that square box and we were applying heat at this point. Okay, maybe let us just take it as the origin. It doesn't matter, you can apply heat anywhere. Okay, so what we have over here is, okay, the heat at different points of this object, it will be different. The temperature at each and every point of this object is different. What I want to say is that the temperature depends on the point, and each and every point can be described by the coordinates x, y, z, right? So the temperature is a function of x, y, and z. For example, if x changes, then the temperature changes. For example, this point over here, okay, where x is changing, is different. Okay, the temperature at this point will be different. You are changing only the x value, the y and the z value, it still remains the same. Okay, similarly, the temperature at this point will be different from the temperature at this point. Similarly, if you go up or even if you go in any direction. Okay, so whenever there is a change, we will be using derivatives. But over here, it gets really complicated. It gets complicated because we have so many directions where there are changes. When we were studying about functions of a single variable, if you remember, okay, we used to draw it something like this, right? A function of single variable, x, and over here the y-axis, something like this. Okay, but now this one, it's a function of so many variables. And when we were doing functions of a single variable, we used to say that the variable y depends on x. So ultimately, what we were changing only the x value. Okay, but over here we will be having something that looks like this. F is a function of x, y, and z. Function of x, y, and z. Okay, so the function changes even if you changes x, if you change only y, and if you change only z. Okay, so that is what is meant by a scalar function. Okay, and over here we are having three variables. Okay, so that okay, so over here we are having a scalar function. Okay, what we want to do is we want to study the change, that is the gradient. Okay, but the gradient, you should remember that it will give you a vector. The gradient of a scalar function, it will give you a vector. Gradient of a scalar function will give a vector. Okay, but what is a vector? And over here, if you remember, whenever we use the word derivative, we used to say derivative at a point, right? So even over here, we will be saying the gradient of a scalar function at a point. It will give a vector depending on that point. But what exactly does it give? Okay, what kind of vector will it give? Okay, again, let us think about this one. Okay, so over here, if we are studying the change of the temperature along the x-axis, okay, so maybe the change in the temperature along the x-axis. Okay, so we can calculate del T del X. If we are studying only the change of the temperature along the y-axis, okay, we can use del T del Y. And if we study the change of the temperature along the z-axis, then we can use del T del Z. Okay, so if we are studying the change in temperature along the x-axis, what do we have to do? We will have to keep the y and the z, y and z as constants. Similarly, over here, if we are calculating this change, we will have to take x and z as constants. And similarly, if we are studying this change, we will have to take x and y as constants. You should take a note over here. We are not using the letter d. Okay, we are not writing it dt dx. Okay, because we are using a special symbol which is called del. Okay, del t del x. Okay, so whenever you are saying del t del x, just remember that y and z are taken as constants. Similarly, for something like this. Okay, so now that we now, okay, that we have understood what we are studying. Okay, we are studying the change in each and every direction. So this is exactly what this gradient will give. Okay, it will give a vector. If the scalar function is temperature, then it will give this one, this vector, plus del t del y j plus del t del z k. Okay, this is when the scalar function is temperature. Then the vector, then the gradient of the temperature at a point, that is the change of the temperature at a point. Okay, the gradient, it is this. It is this vector. Okay, so now that we have understood, okay, let us just go ahead, okay, and write it in a better way. So let's see. So first, again, like I said, we will be needing a scalar function. Let f be a scalar function. Okay, it can be of 2 or 3 variables. It doesn't really matter. Okay, then the gradient of f at a point is a vector whose components are the partial derivatives of f at that point. Okay, do not worry. Okay, when we are doing examples, okay, you will maybe get a clearer idea of what exactly we are calculating. Okay, so the gradient, it is denoted as grad f. Okay, and sometimes, okay, or even most of the times, we can even denote it by, okay, it is denoted by grad f, or by using this one, gradient f. Okay, this one is actually called the del operator. Okay, where del operator or nabla. Okay, and over here it is an operator, so it will consist only of operators only. Okay, del, it can be written as I del del x plus j del del y plus k del del z. Okay, so whenever you write, hence del f or grad f, okay, if you put f over here, you will be getting del f del x I, okay, del f del x I, okay, you can write I to the front or to the back, it doesn't really matter, del f del y j plus del f del z k. Okay, so this is the gradient. Okay, just remember that the components, they are the partial derivatives of the of f. Okay, so this is what the gradient gives. Okay, so now that we have seen what the gradient gives, do not worry, we will be doing some numerical exercises for you to be more familiar. But now let us just understand what is the divergence. What exactly does it give? Okay, the divergence, if you have to study about the divergence and curl. Okay, first of all, what will we need? We will need a vector field. Okay, what exactly is a vector field? Okay, just think of it as a field of vectors. Okay, just imagine that you have a playground and there are vectors everywhere. Okay, the vectors are pointing in this direction. Okay, but over here the field, it may not be flat. The field, it can even be round, or it can be a 3D object. Okay, it can even be a box like this. Okay, where so you have vectors over here, vectors over there. Okay, everywhere we are having vectors. Okay, so first of all, we will need a vector field. That is something that we will need. Okay, to understand what the divergence gives, just imagine this situation. You are pouring water on the board. Okay, you are pouring water at this point, and the water will flow. Okay, the water will flow in every direction. Okay, you are maybe pouring water like this. Okay, then the water will flow sometimes here, sometimes here. Okay, and each and every point it is flowing. Okay, so as you can see, there is some expansion that is going on. Okay, there is some expansion that is going on. The divergence, it measures this expansion. Okay, just remember that. The divergence, it measures this expansion. And over here, I said that we will be needing a vector field. So even though over here flow, it can be represented in terms of the velocity, right? The velocity of the water at this point, maybe it's in this direction. The velocity at this point, again, it may be in this direction, and so on. So velocity, it is a vector quantity. Okay, so there is a spread in the velocity. Okay, so this one will be a vector field and it is expanding, and we will use divergence to measure how much it is expanding. Sometimes, okay, there will be situation where it is even contracting. Okay, so the vector field will be looking something like this. Okay, at this point it is contracting, so even how much is it contracting, we will be using the divergence. Okay, that is for divergence. Okay, now let us think about curl. Okay, from the name only, it is something that is curling. Okay, now imagine this situation. Okay, you are in there is a river. Okay, there is a river, and water is flowing in this direction. Because the water is flowing, so of course there will be velocities. Okay, so you are having a vector field comprising of the velocity of the vector of the water at each and every point. Okay, so you are having a vector field of velocities. Okay, I think you must have noticed that if you are putting an object over here, okay, surely this object will flow over here. But sometimes what you also find is that this object, okay, it doesn't only move down, but it will also rotate. Sometimes as it moves down, it will also rotate, maybe in this direction, or sometimes it will rotate in this direction. So that is the curl. Okay, when we are studying that thing, okay, that it is rotating, we will be using the curl. Okay, so for example, if it is rotating in this direction, so the curl, it will be pointing upwards. Okay, the curl will be pointing upwards according to the right hand thumb rule. And if it is rotating in this direction, okay, it will be pointing downwards. Okay, so again, you will be, the curl itself, it will be a vector. It will be a vector quantity. Divergence, it will be scalar because you are measuring how much is it expanding. Whereas the curl, it will also give you the sense of direction. Okay, how is it rotating? Okay, so the curl, it will be a vector quantity. In fact, you at each and every point, maybe you will be having the curl, okay, will be pointing in this direction and sometimes in this direction. Okay, and at each and every point you can do that. Okay, so actually the curl, you will also have so many different vectors at each and every point. At this point, maybe here, okay, we pointing that direction. Okay, so that is what the curl gives. Just remember these three examples, and then maybe in your higher semesters, whenever you encounter gradient, divergence, and curl, you will have a better idea exactly of what we are studying. Okay, so over here we will need a vector field. Okay, let us just go ahead. Since we are studying with a vector field, we will be writing something like this. Let f be a vector field. A vector field, or it can be called as a vector function of three variables. Okay, then curl divergence f. First of all, it will be a scalar. It is a scalar and it is denoted by divergence f. Okay, but over here we can also write this one in this way, or we can even use the del operator. Okay, we can even use del operator, but over here we will take the dot product with f because we want a scalar quantity. Okay, but also remember that f, because it is a vector field, so f, it can be written as f1i plus f2j plus f3k. Okay, so over here, if you take the dot product del with f, okay, just take a look. You will be having something like this: I del x, because the del operator or the nabla operator will look something like this, plus k del z dot f. It is f1i plus f2j plus f3k. So the divergence, okay, if you take the dot product, you will be having only del f1 del x plus del f2 del y plus del f3 del k. So this is the divergence. Okay, what about the curl? Okay, so this is the divergence. Okay, just take the dot product, you will be having this. What about the curl? Then, okay, I will write here only. Curl of f is a vector and is denoted by curl f, or if we use this operator, we will be using the cross product. So over here we will be having cross. Okay, so if you evaluate this cross product, you will be getting, by using the determinant, ijk del x del y del z f1 f2 f3. Okay, so these formulas, okay, just keep in mind. Okay, so over here, let me just summarize what we had done. Okay, so for the divergence, for the gradient, we are using grad f, divergence f, and we will be having curl f bar. Okay, take note, f scalar, f bar, it is a vector, f bar, it is a vector. This one, it can simply be written as del f. This one, it can be written as del dot f. And this one, it can be written as del cross f. Okay, sometimes they don't even write this vector on top. Okay, sometimes they just write it as del f, del dot f, and del cross f. Okay, do not make a mistake, it is the same thing. Okay, some books, they may write it like this, sometimes they may not write the vector on top. Okay, so with this being said, okay, let us just calculate some numerical examples. Okay, question. Let f, okay, so f, it will be a scalar function of three variables. Okay, maybe xy plus x square z plus x y z cube. Okay, the question is find gradient f. Okay, find gradient f. Okay, solution, you can just write it directly, grad f, or you can write it as del f. Okay, if you remember, gradient of f, it will be del f del x I, it will give you a vector, del f del yj plus del f del zk. Okay, so actually you can do this one directly. Okay, but let me just explain how will you obtain del f del x. Del f del x. Okay, so it will be del x xy plus x square z plus x square y zk. So if you are calculating this one, okay, so you will have to first split it according to the plus sign. Okay, so you'll be having del x xy. Some of you, if you can do it directly, you can do it, but if you cannot, then you can follow these steps: x square y z cube. Okay, so you must remember that we are calculating del f del x. So y and z, they are treated as constants. Because y and z are treated as constants, you can take them outside. Okay, so you will be having y del x x. Okay, similarly z, it is treated as a constant because we are calculating del f del x. Z del x x squared. Similarly over here you can take y and z outside. Y z cube del x x squared. So over here we'll be getting y del x of x, it's 1 because ddx of x, it is 1. So over here we are differentiating with respect to x. It will be 1 plus z ddx x squared will give you 2x. You will be having 2xz. Similarly over here you will be having 2x y z cube. Okay, I hope that is clear. So over here, okay, just write this answer. Okay, now let us just calculate. Okay, just remember this one. Okay, so now let us calculate del f del y j. Okay, del f del y. Okay, del f del y again will be the same thing, del y. Okay, you can skip all these steps if you are comfortable. I keep on repeating that, right? X squared y z cube. Similarly over here, first of all, you will have to split. You will have to split del y xy plus del y x squared z plus del y x squared y z cube. Okay, so over here, remember, since you are calculating the partial derivative with respect to y, x will be a constant. X again will be a constant. Even z will be a constant. So differentiation of a constant will give you 0. Since x and z are constants, it will be 0. And similarly, x and z will be constant. So x squared z cube del y of y. So over here we will be getting x plus x squared z cube. Okay, so this is what we will be getting. And similarly, you can calculate del f del z. Okay, let me do it directly. Okay, if you calculate del f del z of this first term, it will be 0 because there is no z term. For the second one, x squared, you can take it outside, and z you will get 1. Okay, you can do all the steps. Similarly over here we'll be getting x squared y 3z squared. Okay, so this is what we will be getting. So what can you do? You can conclude, therefore gradient f, it will be equal to this term y plus 2xz plus 2x y z cube I. Okay, because if you remember, if you substitute in that equation, we will be getting I plus this one j plus this one k. 3x squared y z squared k. So this is what we will be getting. Okay, this is the gradient of f. Okay, if there is a question, maybe, okay, part 2 of the question. Okay, I did not include this part 2. Hence, find grad f at, okay, this is part 2 of the question, at 1, 2, okay, minus 1. Then what will you do? After calculating up to this part, you will be writing this grad f, and inside bracket 1, 2 minus 1. The value will be, just substitute the values over here. So y, it will be 2 plus 2xz. 2xz will give you minus 2. 2xy z cube. Okay, minus 2 minus 4 I. X will be 1. X squared z cube will be minus 1 j plus And this one, how much will we get? X square again will be 1. Z square will be 1. Okay, 1, 3, 6. Okay, I hope I did not make any mistake. Okay, but in case you do, okay, just substitute the values correctly. Okay, so over here we can just simplify. You will be getting minus 4i plus 7k. So as you can see, the gradient, it can be calculated at any point. You can just change these points, you can calculate. Okay, so this is about the gradient. Okay, now let us just simply calculate divergence and curl. Okay, question. Now we are having a vector function. Okay, f. Okay, maybe x square y I plus y square z j plus x y k. Okay, so now we are having a vector field or a vector function, and it consists of 3 variables x, y, and z. So now we find divergence f bar, and curl f bar. Solution. Okay. Okay, maybe this is part 1. Also find the values. Their values at 0, 0, 0. Okay, so solution. Okay, let us just try divergence f first. Okay, so divergence f, it can be written as del dot f. Okay, so you will be having, okay, so over here, what is f1? F1, it is x squared y. Okay, maybe you can write it down. Okay, here f1 equal x squared y, f2 equal y squared z, and f3 it is xy. Okay, so now we can easily calculate divergence f. Therefore, divergence f, it will be equal to del dot f. Okay, so it will be del x f1 plus del y f2 plus del z f3. Okay, according to the formula of the divergence. Okay, del x f1. Okay, y you can take it outside. You will be having del x squared. Del y f2, z you can take it outside. Del y squared. Del z f3. Okay, it will be a constant, so differentiation will be 0. Similarly, over here we will be having 2xy plus 2yz. Okay, so at the point 0, 0, divergence f at 0, 0, 0, it will be equal to, just substitute x, y, and z as 0, 0, you will be getting 0. 0 plus 0, which is 0. Okay, so this is about the divergence. Okay, now let us calculate the curl of f. Curl f over here will be cross. Okay, curl f will be a vector, so we will be taking the cross product. So over here what we will get, we will be getting I j k del x del y del z, and over here we'll be having f1, f2, f3. Okay, for those of you who can do it directly, you don't even need to write f1, f2, f3. You can just substitute the values directly. Okay, so the next line, okay, I will just erase this part. So f1 it will be x squared y, f2 it is y squared z, and f3 it is xy. Okay, so just expand this determinant. You will be having, okay, I times this one. So I, you can write it outside, so you'll be having del del y xy minus del z y square z. Okay, maybe I will write in better way. Just remember to keep the square brackets. So you'll be having del del y xy minus del z y square z I. Okay, I times this determinant minus j times. Okay, so j times this determinant j, okay, del x, just like you are calculating the cross product, del z x square y plus, okay, whole thing k. Okay, for k will be del x y square z minus del y x square y. So this is what we are getting. Okay, now let us just calculate it. Okay, this will be del y xy will give you y, x you can take it outside, so you will be having x. Over here you will be having y square minus, over here you will be having okay, del x. Okay, so y you can take it outside. Over here del z, so these are all constants, you will be having 0 j plus, and over here you will be getting okay, del x of y square z. Okay, again it will be constant with respect to x, so 0 del y x del y x square y, so x square you can take it outside, so you'll be having this. Okay, just calculate it in a similar way. This one is x squared y. Okay, so you'll be getting x minus y squared I. As you can see, it is a vector quantity minus x squared. Okay. Okay, and if you see the second part of the question at 0 0 0 at 0 0 0, just substitute x, y, and z to be 0 over here. Curl f, it will be equal to the 0 vector. Okay, you will be getting 0i, 0j, 0k, so that is why it will be the 0 vector. Until next time.